Thanks for joining me. Quick clap. So this talk is going to be a tour of the Rust integration work we did for YJIT. There's a lot of complexity in this area to the point where it's almost fractal. Feels like every time you zoom in, there's more detail, right? So we only have finite time today. So I've came up with an analogy to help explain this infinite beast. Right. If you squint a little bit, this is actually wordplay. The talk is about fitting in. You can imagine the Rust part of YJIT, changing schools, moving cities, or maybe even immigrating to a different country. So anyways, I'm going to start by giving you some background, going to why we wanted to use Rust a little bit. After that, I'll talk about aspects of the code base relevant to plugging in the new language. I'll then compare and contrast C and Rust in this context, and talk about how we've handled their differences. To finish, I'll give a simplified model of object file formats and linking that still has a fair bit of predictive power. Okay. YJIT started as a prototype in September 2020 when RNA strands encased in proteins were flying around. Maxine and I named the prototype MicroJIT. It wasn't called YJIT back then, and worked by extending the interpreter at runtime. The C compiler picks a custom calling convention for the blobs of machine code that make up the interpreter. Right? And I wrote a hack to recover that calling convention for use at runtime. The actual code generation mechanism was fairly simple, was basically just straight up templating. You look at what the instruction is, you spit out a predetermined piece of code. If you're interested in more detail, you can check out my talk from last year. After the prototypes showed some success, we got the go-ahead from Shopify to spend more time on the project. And that's what eventually grew into YJIT, and that's what we shipped in Ruby 3.1 in 2021. Aaron Patterson and Kevin Newton joined the effort that year, and John Hawthorne also helped us, John Hawthorne from GitHub. That rendition of YJIT was written in C, like the rest of CRuby, and we pretty much started to port YJIT to Rust at the start of 2020, so soon after we released the first version of YJIT. And in 2022, that's when development really sped up. The team grew a little bit. Noah Gibbs joined us, Jimmy Miller joined us, Kokubun joined us, and we were able to do a lot. We reduced memory footprint and improved peak performance, peak speed. We also added support for ARM chips, important for Apple laptops, and some server deployment. By the time release date came around 5 months ago, so last Christmas, we had enough production deployments of YJIT that we felt comfortable removing the experimental label from YJIT. And that pretty much takes us to present day, May 2023. Okay, so a bit about why we wanted to use Rust. When we started YJIT, the team was new to C. I had some C experience, but not that much, especially in JIT compiler context, and the rest of the teammates also aren't that much experience with C. It seemed like we had a lot of learning to do regardless of the language choice. Rust seemed to have a lot of learning resources, it came out of the box with a bunch of nice tools like, creature comforts such as not needing to declare functions twice, built-in test runner, all that. There's also some more subtler, complex things that it offers, like we had some classes of bugs that we knew that if we talked to the board checker in the right way, we could rule them out at build time. So anyways, Rust is nice for us, but our users probably don't care. A bit of a tautology here to say that Ruby users care more about Ruby than Rust. But I feel that most Ruby users don't really interact with the language that implements Ruby, so underneath. So, if you don't use YJIT, you probably also don't look at the C code that implements Ruby that much either, if you use CRuby. As we'll see in a little bit, YJIT using Rust can actually be a burden for our users. So what do users care about? I think YJIT tries to build up this facade of being able to magically speed up Ruby code, right? We try to boot quickly, so short-lived processes like bundle.exec are still snappy. We also try to be completely compatible with the existing code, so you don't have to change anything to use YJIT. Of course, there's no actual magic here, and like facades for buildings, there are holes that allow you to look into the inside. By nature, generating more code at runtime is going to use more memory than not doing anything, right? But we try to be efficient anyways in service of this facade, right? Being able to obtain YJIT in the first place is also part of that. We care about the end-to-end experience, which leads me to the next chapter. We care about the end-to-end user experience, but there are limits as to what we could influence due to the way users consume Ruby. This environment creates some challenges, and YJIT is influenced by the constraints. If you visit the download page on the official website, ruby-lang.org, you'll see mentions of third-party a lot. This is because really, the only thing officially on offer is the source code. And the page is trying to nudge you to build from source. Yeah. So for many users, the first point of contact with YJIT is actually the Ruby build process. Now, they might not actually be building manually. They might be using some tools to build from source for them, but still, they interact with the build process. And YJIT using Rust directly impacts their experience, right? People now have to install Rust tools in order to get YJIT. And adding to the challenge is the incredible diversity of operating systems Ruby supports. I think this big list from the official website isn't even exhaustive. Also, you can build Ruby with various build configurations on each one of these platforms. So we'll quickly have a combinatorial explosion. Combinatorial. So here are some past build breakages from this diversity. For debugging development, we use a library called Capstone that parses machine code bytes and print them out in a readable format for humans. At one point, we tried to detect Capstone on the system during the build process. Unfortunately, just doing that broke builds for people because the detection code was slightly wrong and it returned the wrong result at the wrong time. And it's just some setup that you couldn't even guess because it's a multi-dimensional configuration space. In the same vein, we have code detecting whether Rust is available for use for YJIT. Now, I tried using echo/n because I was like, oh, in Ruby, if you do double quotes and /n, that's a new line, right? That must be coming from shell. Oh, how naive. It doesn't work like that. It works on my machine like that, but if you look a bit closely, actually different shells interpret it differently, and like the echo command works differently in different shells, so that doesn't work. So I picked these two issues because we deleted code to fix both of them. This integration work really made me develop a taste for these subtractive solutions. With this many options flying around, minimalism sort of becomes a coping mechanism. The way YJIT is distributed kind of stress tests every bit of build system complexity we add. So we try to minimize what we add to avoid breakages. This approach helps serve our users because that's what they interact with when they install Ruby. But it's not without downsides, and sometimes we can go overboard. Let me explain. One dimension of the build configuration space is the make program takes care of calling out the various build tools, including the C compiler. For setup, you write make files in this custom language. You probably use GNU make with the Linux kernel, but there's also BSD make and mmake, different platforms, different dialects. Now, there's still a common small subset of basic features for implementing incremental builds. The general goal is to rebuild quickly by only compiling the code that you changed. It's important during development since you're editing and rebuilding all the time and you don't want to rebuild from scratch every time. For the C parts of CRuby, that's what we use to implement incremental builds. Rust, though, the easiest way is to use Cargo. It's the name of this tool that builds Rust for you. And it just gives you incremental builds for Rust code by default. And that's what we use for development. For the release builds, we don't make users install Cargo, again, to minimize any breakages that might come with that. We just make them use the Rust compiler. Now, notice this bifurcation between the two modes. This can become a build breakage. This can end up as a source of build breakages if we're not careful. So to have minimal differences, I told Make to not worry about caching the Rust build in development. Cargo already gives incremental builds. In release mode, the Rust code would just rebuild from scratch every time. The advantage with this was having just one piece of make setup that works for everything, right? Same code for all the make flavors, also across development and release. One piece of code for everything. So it was nice in this way, and it was nice and minimal, but it was too bare bones. I thought rebuilding from scratch all the time in release mode was fine because it was targeted at users that basically just want to build once and be done with it. They just want to install Ruby. The problem is, we sometimes also need to test and do development in these configurations. For example, to respond to bug reports, because that's the configuration users use. So if they report bugs, we test on it. So anyways, there's a lot of nuances when it comes to deciding what to put in the build process. The maximally minimal solution isn't necessarily the best one. I went overboard with the old setup. We use a more complex setup now, but it's better. So back to the moving analogy, when we're going to a new place or joining some larger organizations, we usually can't influence the environment that much. So we have to adapt. The smoothest Ruby installation experience probably doesn't involve building from source at all, right? There's just too many variables, too many things that could go wrong. But YJIT can't really influence how Ruby is distributed, so we adapt to the environment and we cope with minimalism. Okay. Chapter 3. YJIT has to work with the rest of the runtime system to do its job. And to do that, it has to speak C. It also needs to talk to the operating system. And C is usually the language to do that. So speaking C fluently is very important. Just to put into perspective, here's a diagram that visualizes the amount of C and Rust in the code base. I'm even undercounting some of the C here by excluding some of the headers and some extensions. But even then, you can see how Rust is absolutely dwarfed in the code base. So talking about speaking C, it's kind of like how there's usually pressure in society for minorities to speak languages foreign to them well. Anyways, when talking to C, a lot of the time we're dealing with integers. Rust gives a lot of nice contemporary simplifications. much of it comes from being able to leverage the current hardware landscape. For example, integer types with exact bit widths like U8, I32, U64 are primitive in Rust. But in C, these types are optional, so they're not necessarily there. Like you can't trust that when you're writing C, these types exist. And if you read the C standard, you can sort of infer why that's the case. You can see how the committee was trying to accommodate for implementations that don't use 2's complement bit representation for signed integers, and implementations that have these things called padding bits. So like bits in the integer that don't represent any part of the number. It's like, what? So these machines were more prevalent in 1999 when the standard was first drafted. Nowadays, these machines practically don't exist. So for CRuby, practically, the optionality ends up just being checks that in the build configuration script that never fails, right? Never fail, right? So C wants to support 1999 hardware. What does Rust want? So Rust prefers explicitness in areas that relate to memory safety. Integer overflow has been shown to be a common gadget for security exploits. So unlike C, Rust does not automatically convert between integer types. Here's an example where it shows up in YJIT. Ruby methods implemented in C declare the number of arguments they take with a signed integer. Here are 2 instance methods on the kernel module. We can see here that inspect takes no argument from the 0 at the end. We can see that we can pass a variable number of arguments to the singleton methods method. This is what the -1 at the end means. And you can inspect this number from Ruby. This is the arity of the method. YJIT needs to check against it to implement method calls. Now, after YJIT performs the control flow transfer to the actual C code, the C function might perform some additional checks, but that's sort of outside the purview of YJIT. We just take care of transferring the arguments, and we do the first check, and the C function takes care of the rest. In the implementation for passing the arguments, we inevitably read from some array with an index derived from the arity, which is signed, right? Because you need to accommodate for the -1 case. Now, it's fine to use a signed integer to index in C, and the square brackets are actually just syntactic sugar for adding to a pointer with a number. So if it's negative, you just like go backwards from the pointer and then dereference it. Rust, on the other hand, observes that most of the time you probably don't want to index backwards in that way, and so indices in Rust are unsigned. And if you combine that with the lack of automatic conversion, if you try to just like take the C code and do a one-to-one port to Rust, you get build errors like this. Once you see this, it kind of stops you from doing a one-to-one port because it's kind of like Rust giving you a bug report about your code assuming something that you didn't know about. It then becomes this little puzzle to figure out where to do the conversion in the code and how to do it. And by the way, there are multiple ways to convert between integers and Rust. Maybe for good reasons, because they're different. They have different trade-offs. So this was a source of friction for us while porting. The code I'm quoting from is from invoke built-in. It's not exactly like method calls, so a little bit of presentation, sleight of hand here, but indexing comes up so often in the code that we had to solve a bunch of similar issues. Speaking of frustrations, I'll talk a bit about Rust ownership and reference systems. A common pain point with learning Rust is building intuition with the board checker. When learning a new language, we tried to lean on languages we already know. The best C analogies for Rust references are restrict pointers and pointers to const, which at this point is like, oh, that's already odd because people don't really use restrict pointers in C. You might not even know what it does. It's partly because the rules around restrict pointers in C are too subtle and tricky, and it's hard to review a piece of code and say for sure whether it's following the rules. Much of Rust is designed around machine checking these rules and giving clear messages when these rules around restrict pointers are broken. So, in Rust terms, that's what they call safe, right? The main rule with restrict pointers and immutable references in Rust is that they assert exclusiveness. Basically, you can't have two overlapping mutable references referring to the same thing. Rust will give you build errors whenever it detects this. Now, to do this, Rust uses implicit and explicit lifetime information that gathers from all around the code base and runs it through this complicated constraint solver similar to Prolog, similar to what you might find in Prolog to do it. So it's not really an analysis you can reasonably ask a human to do by hand. The thing about this no overlapping restriction is that it's restrictive. Things like doubly linked lists and graphs cannot be expressed under this restriction, for example. But we do have graphs in YJIT. In fact, YJIT's graphs are very important because we retain them, so they contribute to memory usage consumption. JIT compilers in general actually output more data than code. If you think about it, maybe that's not too surprising because you want the code to be short so that it's fast, but you need the data anyways to handle uncommon situations. So anyways, we have graphs in YJIT. How do we overcome the build errors from the no overlapping rule? Well, we first try using refcell, which tracks borrows at runtime and crashes the whole program if there are any overlapping mutable references. With borrow checking at build time, if a reference has any possibility of overlapping, the checker has to be conservative and say that it always overlap because it just can't know and refuse to build. By checking at runtime at refcell, we can check each individual borrow at the time it happens so that, if at the time there's no overlap, then it's fine. This is how refcell helps with graphs. However, by deferring this check to runtime, it sort of becomes our responsibility to manually do what the borrow checker does at build time. And like I said, it's a hard job because, again, it's really constraint solving, and there's like these implicit lifetime information, and even when they're all explicit, they're scattered around the code base. So it's really hard to do correctly. And no surprisingly, we sometimes got that wrong, and we got crashes from it. The other thing about it is to do this check at runtime, you need some sort of data to keep track of whether a borrow is in flight, right? So it consumes extra memory, and it was eating into our facade of magic. So, the C analogy also kind of shows you how this got a little bit frustrating. The kind of graph representation we wanted to do is probably pretty easy to do with plain C pointers that just don't have any qualifiers like const and restrict, just T star. But with Rust, it's suddenly very hard. So anyways, the current solution we have is to use unsafe Rust, which is its own can of worms because the semantics of unsafe Rust code hasn't been fully decided yet. Rust has an operational semantics team trying to pin down what the exact rules are, when it comes to unsafe Rust. So nowadays, if you want to follow the rules, the first thing you need to do is figure out what rules are already decided and are unlikely to change. It's kind of a messy situation and quite a process. But writing unsafe Rust code today is probably harder than writing unsafe Rust in the future because the uncontroversial rules get their status from being brutally simple. That's why they're like not controversial, because they're so simple you have to agree to them, sort of. The final rule set is going to be more complex, but it's going to be more accommodating. So it would be easier to write code that stay in the final rule set. So I painted a fairly bleak picture here about, using Rust. But I think the general takeaway here is like what to do when like the rules are muddy, right? So what I did here is, find first-party sources as much as possible, read the discussions there, and ask questions. One of the leaders in this space is a professor from ZTH Zurich, Russ June, and they were very generous with their time when I asked questions. It's a little bit of a leap of faith to ask questions, and it does take some effort, but people are nice, and sometimes you just have to ask, and you just have to trust that they'll answer. Anyway, chapter 4, linking. So before I get into it, here's some Unix lore. This is an excerpt from the first edition of the Unix manual from 1971. It even predates the first incarnation of the C language. You can see they refer to LD as a link editors. Nowadays, linker is the more popular choice of the name, but the old name has some advantage in that it's a closer description of what actually happens when you run LD. Now, there's only so much 2 words can convey. For example, you might ask what a link is, but it's still more information. So I'm showing you this because actually this is still like surprisingly relevant. I'm mainly going to talk about, I actually only have 4 minutes left, the linking that happens at build time. So the type that work with files takes in a bunch of files, output one file. Dynamic linking is related to this, but I'm not going to go into detail. So if you go from first principles, this process isn't actually necessary, and nothing stops you from just taking in the source files and outputting the file thing at the end. So like, why have linking as a step at all? And the answer is, it helps during development, so you don't have to rebuild everything from scratch every time. And because linking is a simpler computation than compiling, especially when you're talking about optimizing compilers, hopefully things go faster with incremental builds because you just run the linker, simpler computation. You do run through everything, but you only run the compiler for the parts you changed. So this is what exactly is being edited, and this is the call instruction on x64. The first byte tells you that it's a call instruction, and the next 4 bytes is an offset that encodes what you're calling. It's actually a relative address, so you're never gonna, if you call the same function twice, they're not gonna encode the same because it's never go to this address exactly. It's always go this number of bytes forwards or go this number of bytes backward. But anyways, like you don't actually know, because we've split the code into different object files, you can have situations where you don't know the exact address of who you're calling, and you need to know that to compute this relative address. But at link time, the linker can see all the code at once. So that's how it can resolve everything, and this is actually what the links are when talking about link editing. So what information do we need? So we need to sometimes refer to code that doesn't have an address yet. we need to be able to talk about that. We also need to, on the other side, provide definitions so you can form the links. And then we use a name to link them together, similar to a SQL database. And then you need to, you want to have information to know where to do the patching for those call instructions. So you have that, you say where to patch and how to do the patching. So you refer to the thing we just talked about to do that. And the grand review is that these are symbols and relocation. You can see how linkers have their own lingual. Anyways, so this is just a model. Looks like I ran out of time. But anyways, fitting in is a continuous process, and it's a collaborative one. If you're more interested about linking, I wrote a blog post about the exact issues we ran into, but I didn't even know about these problems, and Nobu pointed them out to me. I think the general message I want to deliver with this talk is that online we're generally reduced to text, but we're actually real humans behind the screens, and you'd be surprised how often people are happy to help if you just talk to them. And it's a little bit weird to do it online, and collaboration sort of becomes, I read your thing, you read my thing, that kind of thing. But I think this fitting in analogy can be helpful if you're looking to get more deeply into open source. Anyways, thank you for listening.